Software-Defined Radio as an Enabling Technology for Cognitive Radio by Scott Boyd. First off, what is software-defined radio? Traditional radios implement radio functions with hardware and circuitry. Today, many circuit functions can be duplicated in software. Software-defined radio attempts to implement all of the functions of radio within one software package. Cognitive radio is an extension of software-defined radio in that it gives the nodes intelligent programming. The hope of this is to allow dynamic spectrum access. On the right here is a diagram of the frequency allocations by the FCC of all the different bands in use. As you can see, each one is kind of blocked off to individual users, and many of those users do not use that band all of the time. So the purpose, or the hope of cognitive radio is to be able to exploit those idle times in those bands and use them, and then when the primary user of that band arrives, then they will vacate and find a new band to transmit it. The networks are self-managing to optimize data flow and rerouting functions. This setup makes much more efficient use of the total spectrum, and since idle channels are utilized. Some of the advantages of software-defined radio is that instead of replacing or modifying existing hardware, you can merely reprogram the original platform. This is in a sense future-proof in that the software can be upgraded indefinitely as long as the hardware continues to function. This makes the time it takes to make large-scale changes smaller, and it also decreases the cost of upgrading such systems. Also, one device can do many different transmission schemes across many bands, so one device can do what it used to take many devices to do. This diversifiability, I guess you could say, also enables widespread compatibility between all the software-defined radio devices as well as other devices that they can interface with. This basically implies a backwards compatibility for such a system, so software could be written in the future to accommodate for this. It's also useful for remote applications that cannot be reached for maintenance upgrades, such as space probes that are halfway across the solar system. Some of the weaknesses of these software-defined radio systems is because they are so easily reconfigurable, malicious software can be easily introduced to a node or a network and spread, causing undesired effects such as interference or jamming. So regulations or policies will be needed to implement it to address this. Also, because everything is done in software, if numerous calculations are required, depending on the application, that can take time, which can cause latency issues. So multiple parallel processors are required to address this. However, that takes up more cost and footprint. The architecture of these systems includes a spectrum sensing element to detect the wireless environment to see if it's okay to transmit or if the primary user has arrived. Many modules working together, such as fast Fourier transform or a demodulator or correlator, are all programmable in such a system, so they can be modified or enabled or disabled. The physical level controller is always in a send, receive, or sense mode, and in each of these modes, different modules are turned on or turned off according to the functions required. And autonomic architecture places the responsibility of network management on nodes instead of a central entity. This requires additional functions to be implemented in the nodes to accommodate, or to, I guess, pick up the slack. This autonomic arrangement adapts far more efficiently as network loads change, as well as the environment. The autonomic nodes sense their environment, determine the spectrum state, plan with optimization in mind, act, and they store the results in an experiential database to, in effect, learn from the situation and improve future responses. One big area to consider with all radio systems is jamming, and software-defined radio provides useful jamming and jam-resisting properties. In one of the papers read, they discuss three different strategies. Strong jamming sends a brief but strong pulse across as many channels as possible to trigger a channel jumping response of a software-defined radio. With light jamming, a weaker signal is sent across several channels simultaneously, covering more bandwidth. However, at the expense of a lower power, it may not be strong enough to trigger the channel jumping response desired. A third strategy is smart jamming, which uses a medium power signal covering more bandwidth than the strong power signal but less than the weak power signal. The goal of this strategy is to block the handshake that happens when a node jumps from one band to another. In effect, if this is successful, the transmitter will jump from one band to the other continuously, unable to begin a transmission. So in effect, all information is blocked instead of just part of the information as in the previous examples. Here are some of the results used modeling existing systems such as the 802.22 system and the military's XG system. As you can just see here, each system has its own response to each individual jamming strategy, and each jamming strategy has a different type of response as well. So you can see the light jamming and smart jamming are fairly similar. There are some small differences with scaling, but for the 802.22 system, the results are fairly close. Another area of interest is beacon research, where we need to be able to measure the effect of the atmosphere on reception on the surface if it's being transmitted from a satellite. The author of one paper modeled this effect using a software-defined radio that they had built, and they compared it against the Moulsley-Villar model of amplitude scintillation. The results are below. On the left, the solid line shows their calculations or their measured amplitude scintillation over the course of a day compared against the Moulsley-Villar model. And on the right, you can see the standard deviation between the model and the data over the course of the entire day, and you can see that there's a big change or a big difference around noon, and the authors attribute this difference to the presence of cumulus clouds that were overhead at the time of the measurements. This implies that those clouds can have a fairly significant effect on what is expected and what is actually received. Another area that requires some research as well for these systems is the ability to do a rapid modulation recognition. With the number of different modulation schemes out there and the complexity of them, this can be difficult and requires some computing time. So in order to kind of cut corners and get to the result faster, they propose a computation ahead of time, and the results are stored in a table. So a simple measurement is done when a signal is received, and it is compared against a number of different entries in a table, and basically the most likely modulation scheme is selected from there, and it is told the receiver is told to use that scheme for decoding, and major time is saved in the process. Also, the incoming data is stored in a buffer while this decision is being made so that no information is lost and the transition is seamless. A very complicated mathematical model is proposed and the author calls the discrete likelihood ratio test, and this uses a concept called the Kramer-Rao lower bound, which has to do with how finely you can measure noise variance of a signal, I guess. For a given estimated noise variance, the likelihood of a given modulation scheme is guessed with this. The resolution of the table, there's a parameter in this model that allows you to make it very, very fine or very, very coarse. This is a good thing to be able to determine because how coarse you make it, or I guess how fine you make it, is proportional to how much memory is needed to store all this information, which can increase the cost and the size, and must be considered. Here's just a plot of some of the results using a few different modulation schemes showing under certain signal-to-noise ratios what is the likelihood of properly classifying a various modulation scheme. And you can see for pretty much all of them used in this particular example, they have basically 100% or close to 100% success around 18 decibels for signal-to-noise ratio. Software-defined radio is very helpful in this, in that it allows many different transmission schemes under various atmospheric conditions to be tested very rapidly. It can be tested under one scheme, reprogrammed within seconds or fraction of a second, and tried again, greatly speeding up the data collection and decreasing the cost as well. In here, the authors focused on the property of amplitude scintillation for their signals, and this is basically the changes in signal power due to the dynamic refractive index of the atmosphere. So as turbulence or clouds or moisture in the air change through the many, many miles of the atmosphere, they have this effect on a signal, and this kind of measures the overall effect of all the layers of the atmosphere together. In the future, some of the ideas proposed in the papers I read, that instead of purchasing a band for use as today happens and bandwidth is extremely expensive, all bands are basically going to be available for the software-defined radio or cognitive radio, I guess, and instead you will be buying spectral access time, as we will be limited by how many people can access all of it at once. Also, radio designers will shift from hardware specialists to software specialists, since most of this will be done with software and far less hardware will be required. I even read of one instance where basically they call it just the software radio is an antenna that heads directly into an analog to digital converter, which heads directly to a processor chip. So there's virtually no need for hardware specialty involved in that, other than potentially the type of processor to use and the shape of the antenna, but analog to digital converters are fairly standard and straightforward. Also, basically, as old devices fade out and new devices take over, as all of them are equipped with this ability, you'll have almost a universal radio platform. So over time, basically every wireless device will have the capability to communicate with every other wireless radio device. With the cognitive radio, we are maximizing the use of the spectrum. Ultimately, extrapolating into the future, you could find a time with even this scheme, you could potentially fill up all of the available spectrum. However, under the current scheme, this is going to happen much quicker than if we transition to this method. Thank you very much.